Okay, section 4.7, of all the sections in chapter 4, this would be the one that I wish wasn't required to cover, because it's probably the most disjointed from the rest of the chapter. We solve problems more or less like we solved problems earlier, but there's a little twist to them, and that twist is it's not particularly hard, but it's a big twist for some students. So just pay extra close attention to the subtle difference between this section and all of the previous sections, because the one small twist makes the problems completely different. And historically, in the past, the problems out of this section, it just caused students a lot of agony on the tests. Like I said, they're not particularly hard, but if you don't kind of pick up on the difference between the problems in this section and the problems earlier in the chapter, and you start mixing them up, then it can get kind of ugly on the test. So just try to focus the best you can on the big difference between the problems in this section and then the earlier problems, and then there's no reason you can't get these all right. Most students do, but students that don't wind up getting an A on this test and get something maybe much less than an A, maybe this section might be kind of the root of their problem. So this section's on conditional probability, and conditional probability is probability based on given extra information. For instance, at the beginning of the semester, if I had to say, what do you think the probability that you're going to get an A in this class is, and then you have some subjective probability, maybe based on your perception of your math knowledge, you might have came up with some percentage of a chance, or based on what you know about Math 142, you might have said, well, I think I have a 60% chance of getting an A, just based on just the knowledge you had to that point. Well, we've taken 3 tests so far this semester, and let's say you've gotten A's on those 3 tests so far this semester, and if right now I asked you the same question, what do you think the probability that you're going to get an A in this class is? Well, your guess, the probability that you guess now, could be different than the probability that you guessed at the beginning of the semester, because you have more information. If you've gotten an A on the first 3 tests, maybe that you might think you've got a 90% probability of getting an A. Well, whereas if you got a C on the first 3 tests, you might be closer to a 0% probability that you're going to get an A. The important point is, if you're given more information to answer a probability question, then your probability could change. Another thing, for instance, if you play like blackjack at a casino, and if you were allowed to wait to place your bet until after you got your first card, if the first card you were given was a 6, you might bet a very, very small amount, because if your first card's a 6 playing blackjack, your chances of winning aren't very high. Whereas if you waited and your first card waited to place a bet and the first card you were given was an ace, well, then you might bet a heck of a lot more, because you've got a lot higher chance of winning if you have an ace as your first card as compared to having a 6 as your first card. So conditional probability is using additional information that's given to you to recalibrate probabilities. And we'll just kind of jump into the section. So conditional probability is the probability that event 2 happens, the probability of event 2 happening given that event 1 has happened. For instance, the probability of you getting an A in this class given that you've gotten an A on the first 3 tests, or the probability of me winning a hand of blackjack given my first card is an ace. So if some information can change the chances of an event happening, and that's what this section is going to focus on. Now, symbolically, we're going to use this symbol to formally ask conditional probability questions. I would read this as the probability of event 2 happening given that event 1 happens. And we used the vertical bar earlier in chapter 1, and I didn't really use it as given that. But in this context, this symbol right here is a conditional probability question, because in general, we had probability questions that look like this. We might, we would just have a probability symbol and then something inside the probability symbol, like the probability of getting a heart. Was this a probability of an event happening, and maybe the probability of event 2 happening with no extra information. This is how it would be presented earlier in the chapter. And in this section, if we get a symbolic question, it's going to look like that. So there are kind of 2 ways to compute conditional probability, and the first way uses a formula that's essentially the same formula that we've been using all this chapter to compute probability. Probability of an event happening is the number of ways the event can occur divided by the number of items in the sample space. But the big difference in this section is that the sample space is going to be reduced to fit the problem. So specifically, to do a conditional probability, we're going to find the number of elements in a reduced sample space that fit the criteria divided by the number of elements in a reduced sample space. So we're going to have to reconfigure our sample spaces to do conditional probability problems. So here's our first example of a conditional probability problem. And generally, if I'm writing a problem that I could call a conditional probability problem, somewheres in the problem, I'm probably going to use the word given. There are other words that I could use to make a problem a conditional probability problem, but given is probably the most common word that will clue you into the fact that this is a special kind of problem that's kind of disjoint from the rest of the chapter. So, first example, a single 6-sided dice is rolled 1 time. Determine the probability that a 2 was rolled given that an even number has been rolled. This is a conditional probability problem because this extra part right here, if this extra part wasn't given, then it wouldn't be a conditional probability problem. So I want to compare 2 probabilities to help you see the difference between traditional probability and conditional probability. So in sections 4.1 through 4.6, we might have asked the question, find the probability that a 2 was rolled or is rolled, and then this compared to the probability that a 2 was rolled given an even number has been rolled. So they're both asking me what are the chances that a 2's been rolled, but from a different perspective. So the top example in black, the sample space for this, when you roll a single dice, if you don't know anything about what's occurred, the sample space is each of the numbers from 1 through 6, because any of the numbers between 1 through 6 could have been rolled in this scenario because I wasn't told anything about what's been rolled. And that will make the denominator for that probability a 6 because any one of the 6 numbers could have been rolled. And then the numerator needs to be the number of items in the sample space that fit the requirement, in this case that a 2 was rolled. So in a non-conditional probability question, a question that didn't have the extra given that something's happened, has been added to the problem, the probability would be 1 in 6. That's not the case for the problem that's in our example, which I've kind of rewritten down here. To do the problem that's been written in our example properly, I need to take into account the additional information, and how I take into account the additional information is I create a reduced sample space. So the reduced sample space for this problem is going to only contain the numbers in the sample space that fit the extra information. So for each of the problems I'm about to do, for the first half of section 4.7, I'm going to create a reduced sample space. And I'm going to use that reduced sample space to get my probability. And the extra information that's given in this version of the problem is that an even number was rolled. So I know that a 1, a 3, and a 5 weren't rolled. And so the only numbers that could have possibly been rolled are the numbers 2, 4, and 6. Now I'm going to use that reduced sample space to answer the probability question. So the answer to this question, which is the same as this question, is going to have a denominator of 3, because given that an even number has been rolled, that means I know that either a 2, 4, 4, or 6 has been rolled. The numerator for this question needs to be the number of items in the reduced sample space that fit the requirement, and the requirement is that a 2 has been rolled. There's still only 1 2 in the sample space, so the probability of rolling a 2 given that an even number has been rolled is 1 in 3, as opposed to in general 1 in 6. So it's basically twice as likely to happen that you'll get a 2 if the first number, the dice that was rolled, was even, as opposed to not knowing anything about the dice being rolled. And this is basically what we're going to do for the first half of the section. Each of the problems is going to be a conditional probability problem, meaning we're going to be given information to take some of the elements out of the sample space. We're going to create something that I call a reduced sample space, a sample space that fits the information that's given in the problem, and then we're going to use that sample space to answer the probability question. So for the first half of the section, my goal is to be able to take the initial sample space, the sample space that would be appropriate if there wasn't any extra information given about the experiment, and create a reduced sample space, and then ignore the initial sample space and use the reduced sample space to answer my question. And then on this next page, I restated the problem as if it was a conditional probability question. And so if it wasn't conditional probability, symbolically it would look like just what is the probability that a 2 was rolled? And the probability that a 2 was rolled without any extra information was 1 in 6. But the probability that a 2 was rolled given that an even number has been rolled, that's the second version of the problem, that's 1 in 3. And the rest of this is just me typing up what I just said. So, next example. A family has 2 children, assuming that boys and girls are equal likely. Determine the probability that they have 1 boy and 1 girl, given the first child's a girl, 2 girls given they have at least 1 girl, 2 girls given that the older one is a girl. This is 3 distinct conditional probability problems, and each part of this example needs its own reduced sample space. So what I'm going to do first is I'm going to create a sample space for a family having 2 children, and then I'm going to reduce it for each problem, each part of the question. I'll say it's a non-reduced sample space because I need the complete sample space before I can reduce it. So in each one of these problems, you see the word given. That means the sample space that's appropriate for a problem without any additional information isn't appropriate to use for our problem. So I'm going to do a sample space for a family having 2 children. I'm going to make a tree. The first child could be a girl or a boy. And the second child can be a girl or a boy. This G represents getting a girl first and a girl second. So one item in the sample space, non-reduced, is having a girl first and a girl second. Done with that G, move to this B. This B represents having a girl for the first child and a boy for the second child. Done with that B, move to this G. This G represents having a boy for the first child and a girl for the second child. Done with that G, move to this B. That represents having a boy first and a boy second. So that's the entire sample space for a couple having 2 children. Now for each of the parts, I need to pick the elements in the sample space that fit the criteria. So for part A, it says, what is the probability that the couple has 1 boy and 1 girl given the first child is a boy? So the first thing I'm going to do is create the reduced sample space. And the reduced sample space is going to contain the elements in the sample space that fit the criteria. So I'm not going to use all 4 elements in the sample space because not all 4 of them have a boy as the first child. This girl and this girl boy, the points in the sample space that have girls first, aren't going to be considered as possibilities in problem A. I'm going to consider only the boy-girl and the boy-boy elements in my sample space. Once I get the reduced sample space, then computing the probabilities exactly the same as what we've been doing. So now that I've used the words after the given to create a reduced sample space, now I'm going to do answer the probability question. The denominator to my probability is going to be 2 because in the portion of the sample space that's appropriate to this question, there's 2 elements. Now I need to figure out, of these, how many fit the criteria of the problem, that there was 1 boy and 1 girl. Well, there's just one of them that has 1 boy and 1 girl. Of the items in the reduced sample space, one of them has 1 boy and 1 girl, while the other one has 2 boys. So my answer to this question is going to be the probability is 1 and 2. The denominator is 2 because there's 2 items that fit the given criteria. The first child is a boy. The numerator is a 1 because within that reduced sample space, there's one of them that has 1 boy and 1 girl. For part B, when I see the word given, I know it's a conditional probability. I look after the word given, and after the word given, it says we know that they have at least 1 girl. That means they don't have 2 boys, essentially. So I'm going to create the reduced sample space. I'm going to abbreviate that RSS. And what I need to do is I need to go through the complete sample space and find anything that fits the criteria that there's at least 1 girl. The first element in the sample space, girl, that fits the criteria that there's at least 1 girl, so I'm going to include it in my reduced sample space. The second element of the complete sample space, girl-boy, there's a girl, so there's at least 1 girl. That needs to be included in my reduced sample space as well. The third element in the complete sample space, boy-girl, has a girl in it, so it fits that there's at least 1 girl, so I'll include it in my reduced sample space. The fourth element, boy-boy, there's no girls, so it doesn't belong in my reduced sample space because it doesn't have at least 1 girl. So for part B, the 3 elements in the complete sample space that need to be considered are the girl-girl, girl-boy, and boy-girl. But I can't consider the boy-boy because it doesn't fit the criteria that at least 1 girl has happened. So now I'm not going to look at the complete sample space to answer my question. I'm only going to look at the reduced sample space. And in the reduced sample space, there are 3 elements, so the denominator of my probability question is going to have a denominator of 3 because in the sample space that is relevant to that problem, there are 3 elements that fit the criteria. Now I go to the left of the given, to the left of the word given. I need to find anything in this reduced sample space that has 2 girls, and that's just this one right here. There's only one element in that reduced sample space that has 2 girls, so my answer to my probability question is going to be 1 in 3. The last part of this example is find the probability that the couple has 2 girls given the older child is a girl. So I need to create a reduced sample space because it has the word given. And the reduced sample space needs to have the older child a girl. And because this is the first kid, I'm assuming that's older, and the second kid is younger. So I'm going to go through each item in the sample space and find the ones that have the older kid a girl. So in a girl, the first child is older, so the first child, the older kid, is a girl. That's fine. This could say the same as, this is the same as the first child is a girl. So girl is going to be part of the reduced sample space. Similarly, girl-boy has a girl first, so the girl is older than the second kid, the boy. So that's going to be part of my reduced sample space. The third item in the complete sample space has the boy older and the girl second. I won't count it because the older child is a boy. And the fourth element in the complete sample space is boy. I won't count it either because the older or the first child is a boy. So of the 4 items in the initial sample space, 2 of them have the older child a girl, 2 of them have the older child the boy. I'm only going to count the ones that have the older child the girl because that was the requirement after the word given. So I've created my reduced sample space. I won't look at that sample space anymore, and now I'll answer the probability question. The denominator is going to be 2 because there's 2 elements in my reduced sample space, and of the elements in my reduced sample space, only one of them has 2 girls, so the numerator is going to be 1. So look at that. Part B and Part C are both asking what's the probability that they have 2 girls, but they give me different information, so the answer is different. In Part B, there's a 33% chance. In Part C, there's a 50% chance. So conditional probability, the probability is going to fluctuate for the same requirement based on the information that's given. The next few pages are just going to help me talk about what I just did. So, given the first child was an idiot. Make sure I have all these right. So 1 and 2, 1 and 3, 1 and 2, 1 and 2, 1 and 3. This is all just what I just did. This is all typing up what I did. 1 and 2. Okay, so now we get to do the homework. I'll do problems, the even problems through 8. You should do the odd problems. And my instructions say create a reduced sample space and then answer the questions essentially. So my first question talks about what's the probability that we give 2 girls, again the same question that we've just answered twice, given the first child is a boy. So first thing I need to do is create a complete sample space, and the complete sample space is for a couple having 3 children. So my complete sample space is going to have 8 elements in it. So I need a complete sample space before I can get a reduced sample space. So I'm going to start out with the first kid, which could be a girl or a boy, or it would be the oldest. A second, which would be the middle, can be a girl or a boy. And then the third, which will be the youngest, can be a girl or a boy. To get this G, it's girl first, girl second, girl third. So one item in my complete sample space is 3 girls. Done with that. To get to that, it's girl first, girl second, boy third. Done with that. Now I'm going to extend this one to have a girl and a boy. To get to this, it's girl first, boy second, girl third. To get to this one, it's girl first, boy second, boy third. Extend this one. It's going to be boy first, girl second, girl third. To get to this one, it's boy first, girl second, boy third. Extend this one. This is boy, boy, girl. And then boy, boy, boy. So for each of the problems between 1 and 8, this is the sample space that we're going to start with. It's going to have 8 elements in it. Now I need, for my problem specifically, to find the elements in the sample space that work. And for me, it's going to be these bottom 4 that have the first child a boy. When you're doing problem 1, you're going to do the top 4. So the first thing I'm going to do in problem 2 is create a reduced sample space, and it's going to contain any element in the complete sample space that has the criteria after the word given, and the criteria after the word given is the first child is a boy. So for me, I'm going to take the bottom 4 elements of my complete sample space and use them to answer this question. For you, in problem 1, you're going to take the top 4 elements in this sample space and use them to answer your question. So both of us, when you do problem 1 and when I do problem 2, when I go to compute the answer, the denominator is going to be 4 because we're both going to have 4 elements in our reduced sample space. Now our numerators are going to be different because I need to have 2 girls, and for me there's only one of the elements that has exactly 2 girls. I'm assuming this means exactly, not at least 2 girls. And your numerator is going to be different. So my answer to number 2 is 1 and 4. Your answer to number 1 is going to be, is it 2 and 4, I guess, because there's going to be 2 elements in the reduced sample space that have 2 girls. Yeah. Whoa. The first child is, that was worded bizarrely, number part 4, so I tweaked how 4 was worded because it was worded bizarre. So for both of us, in problem 3 and problem 4, my reworked problem 4, the information that was given is we know that the first child is a girl. So the reduced sample space for problem 3 as well as problem 4 is going to be the first 4 elements in the complete sample space. So the girl, 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 boy, girl, boy, girl, and girl, boy, boy. So for my tweaked, improved problem 4 and for your problem 3, the reduced sample space is going to have 4 elements in it. The ones that have the girl first, just like it was in problem 1. The denominator needs to have for me, the ones that have more than 2 girls, and for me, more than 2 girls would be 3 girls or more, and I'm only going to have one thing in my reduced sample space that fits the criteria more than 2 girls, so my probability is going to be 1 in 4. For you, for your less than 2 girls, I guess it's just going to be that one. Your answer is going to be 1 in 4, but for a different region, because there's only one of them that has less than 2 girls, whereas there's one of them that has more than 2 girls. Okay, for my problem 6, I need to find the items in the sample space that have a middle child, a girl, and my reduced sample space in problem 6 is going to be different than yours. I'm going to include girl, girl, girl because the middle child's a girl. I'm going to include girl, girl, boy because the middle child's a girl. I'm not going to include the next 2 because the middle child's a boy. I'm going to include those 2, boy, girl, girl, and boy, girl, boy. So you're going to pick through in number 5 the 4 items in the sample space that have a boy in the middle position, so the boy for the middle kid. So once I create my reduced sample space, I know what the denominator of my probability question should be. In problem 6, the denominator of my probability should be 4 because there's 4 items in the reduced sample space. Now I need to find out how many of them fit the criteria that there's one boy. And here there's one boy, here there's one boy. So my numerator is going to be 2 because the requirement is that I have one boy, given that the middle child's a girl. The given that the middle child's a girl makes my denominator 4, and the 2 items within my reduced sample space give me the numerator of 2, and I'm going to reduce this, and for my problem 6 I'm going to get 1 and 2 for an answer. For 7 and 8, we're going to use the same reduced sample space. We're going to pick off this one, that one, that one, and that one that have the oldest child a girl. So after the word given, it tells me I'm only looking at the items in the sample space that have the oldest child a girl. So I'm looking at girl, 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 boy, girl, boy, girl, girl, and boy, boy, girl. So as that's the same part of the sample space that you're going to use for question 7 because they both have the criteria that the oldest child's a girl. Our numerators are going to be different likely. So my denominator for problem 8 is going to be 4 because there's 4 items in the reduced sample space. And now I need to find out in my problem number 8 how many of them have 2 girls. That's 2 girls. This is 2 girls. The other 2, that has 3 girls, that's not 2 girls. That has 1 girl, that's not 2 girls. So I'm only going to count those 2. So my answer is going to be 2 and 4, and I'm going to reduce that to 1 and 2. For you, your answer is going to be 1 and 4 because there's only one of these that has 2 girls, 1 girl. All right. Much harder group of problems, 9 through 16. They're dice problems. And for dice problems, the dice sample space that we've created before has 36 elements in it. So this is rolling a pair of dice, and the sample space, the unrestricted sample space for a pair of dice has 36 elements in it. So I'm going to not recreate this. Hopefully you can actually find this problem 15 in section, I don't know, 4.4-ish. And print out a couple copies of this to do this problem. Will make it a lot easier, so it'd be easier to find the restricted sample space. So this is the sample space that is relevant for problems 9 through 16 that a pair of dice is rolled and the sum of the dice is recorded. So for problem 10, the given part of this is given that the second dice is a 6. So I'm going to go through my sample space. This is first dice, second dice, first dice, second dice, and find all the ones that have a second dice a 6. So this one, 1 6 has a second dice a 6, 2 6, 3 6, 4 6, 5 6, and 6 6. They're the 6 items in the complete sample space that fit the criteria that the second dice is a 6. The rest of the ones that I haven't highlighted, if you look at the second dice, it won't be a 6. So my reduced sample space is going to have the numbers 1 and 6 that has a sum of 7. So this is reduced sample space. The one that has a 2 and a 6, which has a sum of 8. The 3 and a 6, which has a sum of a 9, a 4 and a 6 that has a sum and a 10, a 5 and a 6 which has a sum of an 11, a 6 and a 6 which has a sum of 12. If you're making a stab of doing problem number 9, the portion of the sample space that you're going to need is this row of the sample space right here. That row is a part of the sample space that has a first dice of a 4. So your reduced sample space is going to have 4 1 sum of 5, 4, 2, sum of 6, all the way to 4, 6, sum of 10. And the reason it's going to have those is because yours says given the first dice was a 4. So for the probability in number 9, your reduced sample space is going to have 6 elements, but a different 6 elements than mine. So my denominator for number 10 is going to have 6 elements in it because the reduced sample space, the 6 items, and there are 6 items in the sample space that have the second dice of 6. Now I need to find out in this reduced sample space how many of them have a sum greater than 9. 9 is not greater than 9, 8 is not greater than 9, 7 is not greater than 9, 10 is greater than 9, 11 is greater than 9, and 12 is greater than 9. So my numerator is going to be 3, because within the reduced sample space, there are 3 elements that fit the sum is greater than 9. So my answer for problem 10 is going to be 1 and 2. For number 12, I need to find all the elements in my sample space that have the first dice of 3. And the elements in the sample space that have a first dice of 3 is that row. Any other thing in the sample space, its first dice won't be a 3. So I'm going to write that down as my reduced sample space. For you, your second dice needs to be a 4, so you're going to be looking at that column, the 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, and 6, 4 as your reduced sample space. So my reduced sample space for number 12, reduced sample space, has a 3 and a 1, which has a sum of 4, a 3 and a 2, which has a sum of 5, a 3 and a 3, which has a sum of 6, a 3 and a 4, which has a sum of 7, a 3 and a 5, which has a sum of 8, and a 3 and a 6, which has a sum of 9. So my denominator has to be 6 because there's 6 elements in my reduced sample space. Now I'm going to go to find the ones that have a sum that are odd. That has a sum of 4, that's not an odd sum. This has a sum of 5, it is an odd sum. Sum of 6, not odd. Sum of 7 is odd. Sum of 8, not odd. Sum of 9 is odd. So within the reduced sample space, there are 3 elements that fit that the sum is odd. So the numerator is going to be 3. This is 3 and 6, and my answer is going to be 1 and 2. Oh my Lord. So I'm trying to find the probability that a double is not rolled. I can't worry about that until I worry about the given part. And the given part is given the sum is greater than 10. So I need to worry about this first. Given the sum is greater than 10. So I'm going to go through my sample space and find all the ones that have a sum greater than 10, and the only numbers bigger than 10 that are going to be relevant to me are 11 and 12. So anything here, sums of 2 through 7, 3 through 8, don't matter. For being a sum greater than 10, those are the only ones in my sample space that fit the criteria that the sum is greater than 10. So my reduced sample space is only going to have those 3 elements in it. So my reduced sample space is going to have 5 and 6, which is a sum of 11, 6 and 5, which is a sum of 11, and 6 and 6, which is a sum of 12. Those are the only items in the complete sample space that have a sum greater than 10. So for my question, my denominator is going to be 3 because there's 3 elements in my reduced sample space. My numerator needs to have a double as not rolled, and 6, 6 is a double because both the numbers are the same, and I want the ones that aren't a double. 5 and 6 aren't a double, 6 and 5 aren't a double, and so you get 2 of the 3 elements in the reduced sample space fit the criteria that they're not a double. First thing I need to hammer out in problem 16 is given the first dice is a 3. So I go through my sample space and I find all the ones that have a first dice as a 3, and I call those my reduced sample space. So my reduced sample space is going to have those 6 elements in it, a 3, 1 through 3, 6, and their sums. For yours, given the first dice is a 2, you're going to be using that row for your reduced sample space. So I write down my reduced sample space. Reduced sample space is 3 and 1, sum of 4, 3 and 2, sum of 5, 3 and 3, sum of 6, 3 and 4, sum of 7, 3 and 5, sum of 8, 3 and 6, sum of 9. That's my reduced sample space. So the denominator of my answer has to be 6, because within the sample space that's relevant to this problem, there's 6 elements. Now I have to look at the requirement. The requirement is the sum is greater than 10. That has a sum of 4 that's not bigger than 10. 5, 6, 7, 8, and 9. None of the sums in my reduced sample space is bigger than 10. So there's no items to mark. My numerator is going to be 0. So there's a 0 in 6 chance. The probability is 0. I think 15 is also going to have a probability of 0. All right, now we're moving on to the card probabilities. And 1 card is not as hard as doing 2 for these. So first, for each one of these problems, the initial sample space we're going to look at has 52 cards in it, and we're going to need to find the cards that fit the extra information. So in general, when we're picking 1 card from a deck of cards, our probability has a denominator of 52. That won't be the case for any of the problems between 17 and 24. So for my problem 18, the reduced sample space is going to be, the card is red. So it's going to contain all the red cards. So it's going to contain all the hearts and the diamonds. And I'm not going to write these down because there's too many of them to write down. But I'm marking my reduced sample space in pink. If you counted these up, there's 20, so this is my reduced sample space. So this right here in pink is my reduced sample space, and I don't want to write that down because it's just going to take too much time, and I can use this sheet for my reduced sample space. So there's 13 hearts and 13 diamonds. When I go to do problem 18, the denominator is going to be 26. The numerator needs to be the number of items that are marked in pink, that's my reduced sample space, that fit the criteria. And the criteria is the card is a spade. Well, if I look at all the cards that are marked in pink, that's my reduced sample space. They're either hearts or diamonds. None of them are spades, so the numerator is going to be 0. So this is going to be 0 and 26. The probability is going to be 0. For problem 17, you're marking the same cards for your reduced sample space because you're given the card is not black. The fact that the card isn't black means it's red. So that's going to be your reduced sample space for 17. But your numerator, so when you do 17, your denominator is going to be 26. Your numerator needs to be the number of hearts in the reduced sample space. In the reduced sample space, there are 13 hearts. So your answer for problem 17 is going to be 13 over 26, which is 1 and 2, because your requirement is the card's not black. Those are the not black cards, they're the red ones. That's the extra information to create your reduced sample space. And then within the cards that are marked not black cards, you want to find the hearts, and there's 13 hearts. For your problem 19, you're going to isolate all the spades and the clubs. For my problem 20, my reduced sample space is going to count the face cards, and the face cards are the jacks, the queens, and the kings. So I'm going to mark these up for problem 20. In problem 20, I want the probability a card is a queen given that it's a face card. So my problem 20, the denominator is going to be the number of cards that fit the given criteria. So this is my reduced sample space. This bit right here, these cards for number 20 make up my reduced sample space. So my denominator is going to be 3, 6, 9, 12 in problem 20 because there's 12 cards that fit the criteria that they're a face card. The rest of the cards in the deck don't have a picture of a face on them, so they're not a face card. So now I'm only looking at the cards that I've marked, and I want to fill the criteria that the card is a queen. Well, within the reduced sample space, the things that are marked in orange, there are 4 queens. So the numerator of my fraction is going to be 4 because there are 4 queens of the 12 cards in the reduced sample space. My answer is going to be 1 and 3. All right, what a horrible problem this is coming up. So 22, the probability that the card is not a 7 given it is between 3 and 8 exclusive, meaning can't count the 3 and the 8, only count the 4, 5, and the 6 and the 7. So my reduced sample space in problem 22 are all the cards between 3 and 8, not including the 3 and the 8. In your problem 21, you're including the 3 and the 8 because it says inclusive. So your reduced sample space is bigger than mine. It has 2 more columns of cards to count. So that's my reduced sample space for problem 22. Counts all the cards in the deck of cards that are between 3 and 8, not counting the 3 and not counting the 8. So that's my reduced sample space. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 elements in it. So the denominator of my fraction for my answer is going to be 16 because in the reduced sample space there's 16. Now I'm going to find the criteria. The card is not a 7. So anyone that's not a 7, I'm going to count. So that 4, that 5, that 6 gets counted. The 7 doesn't get counted. This 4, 5, and 6 gets counted. That 7 doesn't. This 4, this 5, this 6, that 4, this 5, and this 6. So within my reduced sample space, that's all I'm focusing on, there are 3, 6, 9, 12 problems that fit the criteria that they're not a 7, and that's going to reduce to 3 and 4. Your answer is going to have a bigger denominator because your reduced sample space counts the 3s and the 8s, so your reduced sample space is going to have 24 in it, and your numerator is going to be bigger because you're going to circle the 3s and the 8s as well. All right, 24. First thing I read through problem 24, it says given my card's a 2. So my reduced sample space is only going to contain the 2s because I'm told the card that was picked was a 2. So my reduced sample space has 4 elements in it. As your reduced sample space will have 4 elements in it, but yours is going to be the queens. Now I need to find out the numerator. The numerator counts all the cards that aren't black. Well, the cards that aren't black are the hearts and the diamonds. So that card and that card are the 2 elements in my reduced sample space that aren't black. They're the 2 red cards. So it's going to be 2 out of 4, which is going to reduce to 1 and 2. Your answer, I think, is going to be the same, just for different cards and different reasons. So one more of this kind of problem, and then we'll get to the second kind of problem in this section that has tables, and we're going to use a formula to do the tables problems. Okay, so assume a hat has 4 bills, so it has a $1 bill, a $5 bill, a $10 bill, and a $20 bill. and I'm selecting 2 bills with replacement. So now I need to make a sample space. Should probably do that on another sheet of paper. So my first bill can be the 1, it could be the 5, it could be the 10, it can be the 20. So I need to have a complete sample space before I could make a reduced sample space. And so I'm doing this with a tree. So the first bill can be any one of those 4, and then it's with replacement. So the second bill can still be any one of the 4. So if the first bill's a 1, I put it back in, and I can still get a 1, a 5, a 10, or a 20 for my second bill. So this would be representing get a 1 for my first bill, a 1 for my second bill, a 1 for my first, a 5 for my second, a 1 for my first, a 10, and then a 1 and a 20. And then if I do the same thing with a 5, make 4 branches out of it for each of the 4 bills that you can get because you're replacing. I would get a 5, then a 1, a 5, then a 10, a 5, then a 5, I skipped, I'm sorry, a 5, then a 5, a 5, then a 10, and a 5, then a 20. Similarly for the 10, because it's with replacement, you can still, after you pull the 10, get any of the 4 bills. So you'll get a 10 and a 1, 10 and a 5, 10 and a 10, 10 and a 20, and similarly for the 20. If you get a 20 first, you can get a 1 second, 5 second, 10 second, or 20 second. So this is a sample space that fits that if a wallet has 4 bills, 2 bills are being selected one at a time, putting the first bill back after you get the second, before you pick the second bill. This is a complete sample space. It's not a restricted sample space. Probably going to need to restrict my sample space to do my problems. So in problem 26, I want to have both bills have a value greater than $5 given the second bill is a $10 bill. So I need to look at my sample space and find all the ones that have the second bill a $10 bill. That's the 1 and 10, the 5 and 10, the 10 and 10, and the 20 and 10. So my reduced sample space for problem 26, my reduced sample space, the ones that have the second bill a $10 bill would be the one that has the 1 and the 10, the 5 and the 10, the 10 and the 10, and the 20 and the 10. So for 26, the denominator of my probability is going to be 4 because there's 4 items in the reduced sample space. Now I'll figure out what the numerator is. Both bills have to have a value greater than 5. That one doesn't count because a 1's not greater than 5. That one doesn't count because a 5's not greater than 5. Both of these count because both the bills are greater than 5. So 2 of the 4 items in my reduced sample space have both bills value greater than 10, greater than 5. So my answer is going to be 1 and 2. What's the probability that the first bill is a 5 given the second bill is a 5? So in my sample space, I need to find the ones that have a second bill of 5. That's that one, that one, that one, and that one. So there's going to be, in my reduced sample space, 4 items. So my reduced sample space is going to have the numbers, the bills, the 1 and the 5, the 5 and the 5, the 10 and the 5, and the 20 and the 5. I'm counting those because those are the 4 items in my reduced sample space that fit the criteria that the second bill is a 5. So now I've done with that part, and I want to look at the ones of these that have the first bill of 5, and this is the only one in the reduced sample space that has a first bill of 5, so my numerator is going to be 1. Okay, that's the first half of the section. I don't know if it's the easier or the harder half of the section. It's definitely the part of the section that takes more work because I have to create a complete sample space, filter it down to a reduced sample space to answer my questions. The rest of the problems in the section, the problems when you see them, they're going to have tables in them. Somewhere we'll get to the homework. There's a table, 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 and that's it. So when the problems have a table and they're conditional probability questions, I'm gonna attack the problems by using a formula. I used to teach the problems without doing a formula, and I used to try to make the problems fit what we've been doing for the first group of problems, but I had bad luck with it, and so I'm trying the formula this time through and hoping it's better. So there's a formula for the table problems. So for the table conditional probability problems, again, you'll be able to tell that they're conditional probability by the way the problems are worded. And the formula is going to be the number of ways both events can occur together divided by the number of ways the given event can occur. That might not help, but I don't want to go through that. I'm just going to jump into the problems and show you how to do it. So here's an example. So 200 patients who had either hip surgery or knee surgery were asked whether they were satisfied or dissatisfied with the results of their surgery. So some were some of the knee people were satisfied, some were dissatisfied, hip satisfied, dissatisfied. It turns out that, well, if you have older parents and they start talking about these things, that knee surgery, getting knee replacement, it's a horrible surgery, and the recovery takes a long time, and a lot of times people still have pain in their knees after they have the surgery, even like a year out. But hip surgery, even though it seems like it's a more involved surgery, the recovery period is way quicker and people are generally happier. So I made these numbers up based on what I know. So they're just guesses. So as I read through my question right here, I'm going to attack this using the formula, and I'll show you what the formula is here in a second after I read the problem. So if one person from the 200 patients is selected at random, determine the probability that the person was satisfied. So up through here is just probably not going to help me. It's not a probability question. The probability question comes from here. The probability that the person was satisfied, that's the question that we're being asked. Is the person satisfied? And then the conditional part is, given the person had knee surgery. So we're going to attack this working the given part first. So the first thing I'm going to do is look to the word after given and find out how many people this represents. So I'm going to isolate all the people that fit the criteria that they had knee surgery. And that's this row right here. So this is kind of my reduced sample space. So these are all the all the people that fit the criteria that they had knee surgery. The denominator for this probability is going to be 95 because I'm not looking at any of the people that had hip surgery, and I'm not looking at any of these totals on the bottom because those all include people that had hip surgery. So I'll look through the table and I'll look in my problem after the word given, and I'll isolate the portion of the table that is focusing on. So I'm only focusing on the 95 people that had knee surgery. That's going to give me my denominator. So I look at either the row or the column of the table that is being talked about after the word given, and I'm either going to, on my first step, I'm either going to isolate a row or I'm going to isolate a column. And in this case, I'm isolating a row because I'm given the people that had knee surgery. So I'm not looking at any of the table anymore and only looking at that column. Now I want to find the probability that the person was satisfied. So within the people that had knee surgeries, I want to find the number of people that were satisfied, and that's the number that's going to go in the numerator. So this is going to be 70 and 95, I'm just going to reduce that fraction. First time I need my calculator today. So 70 divided by 95, math, enter, enter. I'm going to get 14 and 19. So for each of the table problems, I have a more elaborate write-up written, but for each of the table problems, what I will do is I will isolate the portion of the table that applies to the given information, and then ignore the rest of the table, so completely just don't even think about the rest of the table, and just use that column and to answer the probability question. There's a long write-up that's really technical, and I wrote my answer as a percent. We've only ever been writing answers as reduced fractions. It's not wrong to write answers as percents, and in some sections maybe it's even appropriate, but I'm going to give my answers as reduced fractions because that's what I do consistently. I think in the next section I give some percent answers just because you might see them in a different class. Oh, damn. So now I want to do part B, and part B of this says, for this table that I just destroyed, which was really unfortunate, what is the probability a person was dissatisfied given they had hip surgery? Well, immediately I see the given part, the given that they had hip surgery. So I need to go to the hip surgery row. I'm going to write it down here because I destroyed it. And in the hip surgery row, because that's what I'm going to look at here, we have a satisfied, which were, I think that's 90. Idiot. Let me just do this on another sheet of paper. So I'm going to look at part B. In part B, it was given they had hip surgery. So I go to my table and I focus on the hip surgery row. And the hip surgery row had a satisfied, a dissatisfied, and a total. So the only portion of the table I'm looking at is that portion, and it goes 90, 15, 105, not that it's probably readable anymore. So first step is read through the problem, find the given information. In this case, the given information was the person has hip surgery, and then bring out the part of the table that fits that criteria, and the total from that column is going to give me the denominator for my probability. So the denominator for my probability is going to be 105. Now I'm going to go get the numerator. So I go to the left of the word given, and I want the probability the person was dissatisfied. Well, within the set of people that have had hip surgery, only 15 of them were dissatisfied. So this is going to be 15 and 105. I guess I'm kind of doing this without a formula. I'm using a formula, but you're not seeing the formula because the formula is probably more complicated than it needs to be. So the probability here is going to be 1 in 7. And this whole write-up gets me to there, but it's much more complicated. Ugh. Okay, last problem, hopefully, because I destroyed this table. So last thing, what is the probability that someone had knee surgery given they were dissatisfied? So what I need to look at now is the portion of the table that fits the given. And the portion of the table that fits the given was this dissatisfied column. So I'm going to bring this dissatisfied column and make it live here. So the dissatisfied column has the numbers 25, 15, and 40. And to the left of the 25, it was for the knee surgery. For the left of the 15, it's hip surgery, and then it's a total. So this is the portion of the table that I need to look at in part C, because I was given the person was dissatisfied, so I extracted the dissatisfied part of the table, and I'm going to use it to answer my question, and I probably needed the words over here. So immediately I'm going to make a fraction, And the denominator of the fraction is going to be the total of the column that I had to pull. So I'm pulling the dissatisfied column. There are 40 people in that dissatisfied column. So I'm done with the given they were dissatisfied. That told me to pull the dissatisfied column, yank out the total for the denominator. Now I look to the left of the word given. To the left of the word given, I see they've had knee surgery. So within the dissatisfied column, I want to isolate how many had knee surgery, and it's 25. So the numerator is going to be 25, and this is going to be clear. 25 divided by 40 equals, that's 62.5%. Math, enter, enter. It's going to be 5 and 8. This is how we're going to handle the table problems. Got exactly the same problems. Again, this write-up would probably be nice if we were like getting higher in math and needing the symbolism, but I think it's a little much for right now. All right, so this table, I have to understand what the table has presented before I can figure out what part of the table I need to answer my question. So at a zoo, a sampling of children was asked. Word feels like right, but was what word wanted, and it's got to be correct because my English skills are not great. Anyways, a bunch of children at a zoo were asked if the zoo were to get one more animal, would they want the zoo to get a lion or an elephant? So this zoo is debating between adding a lion and adding an elephant. They asked a bunch of boys and girls what they would want the zoo to get for one more, if they were going to get one more of these animals. So I'm going to answer the questions. So question 30 says, what is the probability that the child was a boy given the child preferred an elephant? So immediately I know I'm looking at this portion of the table, because this is the portion of the table that fits the given. So when I go to do my fraction, the denominator is going to be 195, because the portion of the table that's being called out by the given is the given the child preferred an elephant. So that's going to be the denominator. And now the numerator is going to be the number of kids that fit the criteria. And the criteria is a child's a boy. There's 110 in this part that I highlighted that were a boy. So it's going to be 110 over 195. Gives me 22 and 39. I'll walk you through your problem real quick. For your problem, your given information is the child is a girl. So you're going to look at this portion of the table, and your denominator is going to be 160, because within the portion of the table that you're asked to focus on, the total is 160. Your numerator, so you're not looking at that, you're only looking at the girls, and you want the child selected a lion, 75 in that row selected a lion. So it'd be 75 over 160, and then whatever that reduces to. For 32, I'm focusing on given a girl, so I'm going to focus on the girl row. For 31, you're focusing on preferred the lion, you're going to focus on that column. So for 31, your denominator is going to be 165, because you're told the child preferred a lion and you're only looking at the lion column. I'm told the child's a girl, so I'm only looking at the girl row. The denominator of my fraction in problem 32 is going to be 160. And now I'm not going to look at any of this. I'm not going to look at any of this. I'm only going to look at the girls and find out how many of them prefer the elephant, and that's going to be 85. So my answer is going to be 85 and 160. Math, enter, enter, and that's 17 and 32. For you, you were focusing only on the lion, because the child prefer a lion, so your denominator is going to be 165, and then so you're not looking at any of those columns, and you wanted to find the number of girls in that column, your numerator is going to be 75, because within the line column there were 75 girls represented. And then reduce it. New table, much more advanced table, but it's okay. We can deal with it. So, quality control inspector is checking a sample of light bulbs for defects. So the quality control inspector picked 20-watt bulbs, 50-watt bulbs, and 100-watt bulbs to check. Some of them were good, some of them were defective. Most of them were good, because you wouldn't like to have too many defective bulbs. So, first question, what is the probability that if a light bulb is selected at random that is defective given it is 50 watts? So for my problem, I'm going to look at the 50-watt row. And the 50-watt row has a total of 105. So my denominator for problem 34 is going to have 105. When you do 33, you're going to look at the 100-watt row. Your denominator is going to be 130. Now I'm only looking at the part that I highlighted, and I'm trying to find how many were defective. And in the part that I highlighted, there were 5 defective. So it's going to be 5 and 105. Your answer, you're only looking at the 130 in the 100-watt row, and you want the 120 good ones. So 5 divided by 105. Math, enter, enter, and I get 1 and 21. For 36, I'm only looking at the defectives, because after the word given, I see defective. So I'm looking at those. So in 36, my denominator is going to be 30. Your denominator is going to be 300, because it's given that it's good. And now within this, I need to find the ones that fit the criteria that they're 50 watts. There are 5 of them that were 50 watts, so I'm going to get 5 over 30. I think that reduces to 1 over 6. Do it. Yeah. So hopefully you can figure out you're only looking at the good ones, so you're looking at that column, and you want to find the number of 100 watts in that column, which is the 120. Last group of problems. A survey of students was determined if they had a pierced ear. The result is summarized in this table. So for guys, 36 had pierced ears, 144 didn't. Females, 288 had pierced ears, 32 didn't. All right, so one person is selected at random. Find the probability. So for 38, find they were male, given they were not pierced. So for 38, I'm going to look at this column of people that were not pierced. So my denominator is going to be 176, because there's 176 people represented in this column. My numerator is going to be the number of in this column that were male, which is 144. So it's going to be 144 over 176. And then math, enter, enter. I get 9 and 11. For you, you're going to be looking at the pierced column. So your denominator is going to be 324. And then your numerator is going to be the females within that column. I think the last problem is here. For 40, it's given that they were male. So I'm going to go to the male column, row. Only focus on it. The total in that row is 180, so my fraction is going to have a denominator of 180. And my numerator needs to be the number that were not pierced. And for not pierced, it's going to be 144. So I'm going to get 144 over 180. And that's 4 and 5. All right, felt like a really long lecture, so hopefully I didn't lose you along the way. The next 2 sections are kind of don't fit in so well with the rest of the chapter as well. I don't always test on those, so check the syllabus to make sure if you have to do those or not.